We have seen how we can use the normal distribution as an approximation to the binomial distribution. In this video, I want to investigate the similarities between the normal distribution and the Poisson distribution. Well, it makes sense, first of all, to look at the mean and variance for the Poisson distribution. If I have a Poisson distribution P0 lambda with mean lambda, its variance is also lambda. So it seems sensible if we compare the Poisson distribution with mean lambda with the normal distribution with mean lambda and variance lambda, so that both distributions have the same mean and variance. Well, let's start by looking at the Poisson distribution with mean 2.5 and the corresponding normal distribution with the same mean and variance. If we look at this, the Poisson distribution, the Poisson probability histogram, the red rectangles are very definitely not symmetrical. The normal distribution is symmetrical. We lose a bit of it over there. So really, it doesn't compare very well with a mean of 2.5. Well, let's move on. What happens if we look at a Poisson distribution with a mean of 5 and the corresponding normal distribution with the same mean and the same variance? Well, it's better than the previous one, but the Poisson distribution, the probability histogram, is not symmetrical. There's quite a tail up this end. So better, but still not something that I would like to use. Move on. If we take a Poisson distribution with mean 10 and the corresponding normal distribution, we are getting much better. There's still a slight tail up here compared with the other end, but the agreement is better in the middle. Moving on again, increasing the mean, a mean of 20. This now is beginning to look really quite useful. Yes, we might detect a slight tail there, but very slight. Much, much more similarity between the normal curve and the red rectangles. Moving on again, 100. I don't need to point this one out to you. I mean, now the agreement between the curve and the red rectangles is very close. So as the mean, as lambda gets bigger, so the agreement, the link, the similarity between the normal distribution and the Poisson distribution gets better and better. In fact, what we do is this. If we have a Poisson distribution, we know, as I've said before, that the expected mean is lambda, the variance is also lambda. If lambda is greater than 10, then we use the normal distribution n lambda root lambda squared as an approximation to the Poisson distribution with mean lambda. So it is just this condition here. If lambda is bigger than 10, the bigger lambda is, the better the approximation. Okay, let's move on. Let's suppose we have now an example. Cars arriving at a filling station at the rate of 18 every 5 minutes. Find the probability that at least 23 cars arrive in a 15-minute period. At least 23. So we are looking at the probability that x is greater than or equal to 23. Well, 23, that would be a lot of tedious arithmetic. We want to use a normal approximation. Exactly the same as when we had the binomial. When we start using an approximation, which is a continuous curve, we have to be very careful about where we start. We want to start here. We want to include 23. If I want to include 23, I must start where the purple cross is, and I must take the area which is above 22.5. Now that's the same idea as we had with the binomial. It's called a continuity correction. We're using a continuous curve to describe a discrete population. The numbers of cars can only be 22 or 23 or 24. A histogram has to be continuous. The normal distribution is continuous. The only way we can include 23 is to start at 22.5. Don't be careless on that one. Okay, let's move on then and do it. We're looking for the probability that x is greater than or equal to 23. We are going to use the normal approximation. So let's put that in. X twiddle p naught. I've got the bracket in the wrong place. 18 approximate with y twiddle n 18 root 18 squared. So probability that x is greater than or equal to 23 would be difficult to work out. It's approximately the same as the probability that y is greater than 22.5. Remember, it makes no difference whether I write greater than 22.5 or greater than or equal to. I can use either. This is equal to the probability that z is greater than or equal to 22.5 minus the mean, which is 18, divided by the standard deviation, which is root 18, which gives us probability that z is bigger than or equal to 1.06. If we look that up in the tables gives us the area up to 1.06. That's 1 minus 0.8554, which is 0.1446. We give 4 decimal places because we have used the tables. Very simple, not very different to using the binomial. Once you've decided what approximation you're using, everything follows. Well, that was part A. Let's look on and look at part B. The probability that at least 46 cars arrive in a 30-minute period. We were dealing with a mean of 18 cars in 15 minutes. So in this situation, we now have lambda is equal to 2 times 18, which is 36 cars in 30 minutes. So we're now dealing with x is a random variable with a Poisson distribution of mean 36. Once again, life is tedious if we will try to work that out accurately using the formula lambda to the r e to the minus lambda over r factorial several times. But we can approximate with y, a normal distribution with the same mean and the same variance. Well, the variance is the same as the mean, which is 36. The standard deviation, therefore, is 6. The variance is 6 squared. Now we're looking for the probability that x is greater than or equal to 46, at least 46. That is approximately the same as the probability that y is greater than, if I want to include 46, I must have 45.5, and it really doesn't matter whether I write greater than or equal to when I'm dealing with a continuous function, the normal. This is equal to the probability that z is greater than 45.5 minus the mean divided by the standard deviation, which is the probability that z is greater than 1.58. Again, the tables work with the probability up to 1.58, so this is 1 minus 0.9429, and that is 0.0571. 4 decimal places again because we're using the tables. Notice that we can't even start to think of using the idea of 23 in 15. 46 in 30, this number 0.0571 has no bearing at all on the probability of 23 in 15, which was 0.1446. Just not connected. And the last part, the probability that at least 23 cars arrive in each of 2 15-minute periods. Well, how are we going to do that? We want the probability that there are at least 23 cars in the first 15 minutes and at least 15 cars in the second 15 minutes. Well, we worked out in part A the probability that we had 23 cars, at least 23 cars in 15 minutes. That is 0.1446. The probability of getting I've written 15. I should have written 23. So the probability of having at least 23 cars in the second 15 minutes is going to be the same. "23 in the first 15 minutes, 23 in the second 15 minutes. The periods of time are independent. So my 2 events are independent. I can multiply the probabilities. And when I do that, I get 0.0209. This time I give 3 significant figures because I've used my calculator. Don't forget that when you're using the normal distribution to approximate a binomial or to approximate a Poisson distribution, you must use a continuity correction. That means that if you have the probability that x is less than or equal to 4, that is going to be approximately the same as the probability that y. Now, if we want to be less than or equal to 4, we've got to include 4, so we must come down from 4.5. Doesn't matter whether I write less than or equal to when I'm using the normal. If I want the probability that x is less than 4, that's approximately the same time. This time I don't want to include 4, So I have the probability that y is less than 3.5, or, and it doesn't matter, as I say, whether you put the equals in or not, because y is from a normal distribution, y is continuous. The other way around, if I have the probability that x is greater than or equal to 10, that's approximately the same as, think of those red rectangles, I want to include the rectangle with 10 in. I must start at 9.5. And it doesn't matter whether I write one or the other. And if I want to take the probability that x is bigger than 10, this time I don't want to include 10. If I start at 9.5, I include 10. I've got to start at 10.5. And again, I can use either of them. A lot of people just rush into this. You cannot think, I'll always subtract a half, I'll always add a half. Depends very much on whether you're less than or equal to, or less than, or greater than or equal to, or greater than. There is no consistent adding and subtracting a half. The best way to do it is to think, what does it mean? That is vital. Don't forget it, and don't be careless when you're using it. You will find more about this in your textbook, S2, on pages 86 to 88.